Hey, I'm just going to quickly run through a few of the basics of the spectrum analyzer, hopefully answer a whole bunch of questions and maybe give you some neat tips and tricks for getting the most out of it. So I'm running this in demo mode at the moment. This is particularly useful if you just want to try out the instrument without actually having a MokuLab. So you can run this on just an iPad. You don't need any instrument or any devices connected to a network. So basically what we've got here are just two input channels being simulated. The red one, the input 1 signal, is just a signal that is oscillating between two frequencies very slowly. And then the second channel, the blue one here, is just appears to be a signal at 150 megahertz with two sidebands on it. So what we'll do is get started going around all the different features. So up the top left, we have this little main menu button. This allows you to go through and select different devices, select instruments, save and recall settings. This is cool. So if you wanted to, for example, so what I'll do here is I'll get some different settings applied, and then what I can do here is save that current state. What I could then do is go back to whatever I had it at, like this. And then if I want to go back to that load save state, then it'll actually bring me back to that exact configuration. And that can be handy if you want to quickly snap back to a very specific or predetermined instrument configuration. You can also access files. So this is useful if you've saved a whole bunch of data and you want to basically manage it all. And then you've also got things like changing light mode. So if you work in a dark lab, this is a lifesaver because you won't go blind. But most of the time people will just want to use it on light mode because it looks pretty cool. And also things like external 10 megahertz reference clock. So this is important because if you connect an external 10 megahertz reference to MokuLab, it'll automatically detect that. It'll phase lock to that reference. But if you didn't want it to do that for any reason, you can force it to use the internal clock. The next icon right at the top is a little cloud symbol. So clicking on that, this is brings up the ability to save data to CSV or MATLAB files, depending on what you want to do. We can save the settings. We can save a screenshot if we want. We could change the name of the file to whatever, something imaginative. And then the other thing we can do is select the destination. So, you get a SD card with MokuLab, so you can save it to that. But a lot of people actually save to Dropbox, or alternatively, it's becoming increasingly popular to save to My Files, because then you can basically just store all the data locally on your iCloud account through the iPad's onboard storage. So to resume a measurement, you'll notice that there's a little play button down the bottom here that is, sort of drawing our attention towards it. It's because in order to resume the measurement, we have to click it. And so we might as well explain this. So if you wanted to pause a trace for any reason to take a measurement, then you just hit the pause button and then resume. All right, so the next icon that is worth noting is the hide and show the settings panel icon. So this is this one up the top right here. So if you didn't want to see all the settings, you can just hide it. This gives you maximum screen real estate for looking at your traces. To reveal it, you basically just tap it. And what it does is it brings up this little measurements panel with 3 different tabs. The first tab is basically how you set up each of the different inputs. So we can select things like voltage scale, the reference level. These are generally actually the scale and the ref level are most easily configured using gestures. So you'll notice that I can pinch and zoom, and I can pan around, and I can pinch sideways to change the span. But the other thing you can do is if you put 2 fingers on the screen and then move up, it'll zoom all the way out. And if you pull them down, it'll zoom in. So that's a nice quick gesture for very quickly, changing the scale and span. You can adjust the input coupling from AC and DC. If you've got AC coupling engaged, then it just basically high pass filters above 90 hertz. That's useful if you basically want to reject a whole bunch of DC noise. You can select between 50 ohm and 1 mega ohm impedance. So depending on what kind of system is being interrogated, you want to set the impedance appropriately. And then the final option here is the attenuation. So you can't see it in demo mode, but generally, if you've got a very high amplitude signal, then you want to run on 20 dB attenuation to make sure that you don't saturate the input analog to digital converters. So we can turn channels off, we can turn them on just with these slide switches. We can also look at a math channel, which is kind of cool. So I could do, for example, a max hold. And what this is cool for is that it'll actually allow me to very quickly measure, things like the modulation depth of this, whatever this, signal or channel one's doing. So, it looks like it's about 20 megahertz. The other thing that you'll notice down the bottom is that you can change the units in which you view data. So, we can look at it in a linear scale, so volts, and you'll notice that the noise is very low in this view, but most of the time you're actually interested in these small features, so you look at it on a logarithmic scale in dBm. But you can also view these traces in either in units of power or power spectral density. And so the power spectral density is useful because it basically normalizes the power to the resolution bandwidth, which I'll get to in a second. So in the frequency menu, you've got settings such as the start frequency and the stop frequency. That dictates the span. So you'll notice down the bottom here, I've got 35 megahertz. Well, I can make that, let's just say 50 megahertz, and I can make this one, let's say 180 megahertz. And this is a really, really quick way of just adjusting the span. But again, the other way you can do it is just using pinch gestures. It's really like the nicest thing about MokuLab's interface is that, you don't have to mess around with knobs or buttons or anything. In contrast, for example, to an electronic spectrum analyzer by Keysight or HP or Agilent, in order to change the span and, the center frequencies and all this, you have to go through menus and turn knobs, and, it's quite a difficult process. And, especially it's a very time-consuming process a lot of the time as well. The next thing that you can select here is resolution bandwidth. So we have 3 modes here. One is auto, in which case we just figure out a nice setting for you. You can manually set it. So for example, if I wanted to set this to a 2 megahertz resolution bandwidth, then I can do that. But then there's also a minimum setting. So if I want to basically just have the maximum resolution possible given the current conditions, for example, the span and all this, then I can just set it on min, and I can't, for example, in this mode, set it to 1 hertz because the minimum possible resolution bandwidth is calculated to be about 123.2 kilohertz. But if I were to zoom in, you'll notice that number is now changing. So as I reduce the span, so for example, if you're looking at signals at low frequencies, you'll be able to pick out more fine details because you'll be able to get a much tighter resolution on your spectrum. So I'm just going to zoom all the way out. And so that was an interesting thing. I didn't know about that, but turns out that central peak at 150 megahertz actually has some structure. So what a nice little surprise. So the other thing that we can do is change the windowing. So I'll just go back to this. So you can select from 4 options. One is no windowing. So this is, you could expect quite a lot of spectral leakage in this. You can select a Hanning window, Blackman-Harris flat top. It depends on what you're actually trying to measure, but most of the time Blackman-Harris is a pretty versatile window. This is important just for basically making sure that what you're actually seeing in the spectrum is signal and not just an artifact from the hybrid super heterodyned FFT algorithm that we use. You got a video filter. Really not sure what to go with that is. I don't personally ever use it, but I imagine it's just a nice way of smoothing out different features. Averaging is very useful. So if I turn that up, you'll notice that the noise on the bottom here is basically just sort of melts into this single line, whereas if I turn it off, it's quite bubbly and dynamic. So averaging is really, really handy if you want to essentially reduce the noise and maximize the clarity of the signal that you're observing. And then persistence is cool because Again, it allows you to see what a signal is doing over a different periods of time. So if I set this to 3 seconds, then it gives you a very quick reference as to how that signal is changing over different time scales. So if I go to 1 second, for example, I can see that this peak is moving at maybe a few hundred millihertz or something like that. All right, the final one is also a really neat feature of MokuLab's spectrum analyzer. So we have this ability to synthesize waveforms at the same time that we're measuring them. So I could, at the same time that I'm measuring signals on the inputs, I can generate different tones. So I could generate one at anywhere from basically DC up to 250 megahertz. And I'll make this one 1 millihertz. I can set the amplitude. It's nice because the interface is basically designed to try and make things as easy as possible. You can select units. It's pretty great actually. So this swipe to adjust thing, you just slide your finger around it, and what it'll do is just update that value, or as you saw before, just type the value in directly. All right, sweet. So now that that's done, we can have a look at some other stuff. So you may have noticed earlier that I dragged some cursors into the measurement window. MokuLab's user interface makes this trivial because you just tap this icon here and you can add a power cursor. If I tap the blue trace and add a power cursor, it'll add a different one there. I can add a frequency cursor, and this is obviously common to both of the traces here. So what I'll do is I'll just set that one. I might set that one to 150 megahertz. And what I might do actually is we'll use this one because it's kind of cool. What I'm going to do is set the minimum resolution there. I'm going to turn averaging up a little bit. And what we're going to do is remove that red one. And I'm going to set this label to track the maximum. And so what that'll do is that cursor will now basically always follow the maximum peak. I'm going to also show you how to very quickly add. So you can just tap the icon and then just drag, add power cursor. But the other way is just hold that little icon and then drag up, which is pretty sweet. And so what I'm interested in here is two things. So what I might do is set this as a reference. And now what it's showing me is that my signal at this 150 megahertz is 49.5 or so dBm per root hertz. So in power, it's about 95. That's wrong. It's about 50 dB, which is awesome. It's pretty good. So that's one way of measuring signal to noise, for example. But the other thing that you can do, which is kind of cool. So if I turn averaging down, what I'm going to do is go back to auto. Might turn averaging up. No, I can't do that. I'm just going to quickly remove that one there. I'm going to leave this cursor to track the maximum peak of the second channel. But what I might be interested in, for example, is tracking or logging the frequency of whatever this this red tone is. And so one of the things I can do here is if I tap this icon down the bottom right, it'll bring a marker into view like this. So what I can do with that marker is just say, well, on red channel, so on channel 1, track the peak. And what it'll do is lock to that peak. And you see it's got a label here. That label is marker A. And what we are going to do is if we tap this, and I tap this little measurement here, so this is currently tracking the peak level. If I say I want to track a marker and not necessarily one of the channels, then what I can do is say, show me all the different markers that are available. I've got one marker called A, and I want to measure its frequency. And so you can see here that I've got now this measurement down the bottom of what that frequency is actually doing, right now, which is pretty handy. So I could drag a cursor onto the blue one as well. So I just drag it up there, and I could say, just track the maximum. Or in track peak, I can drag it down to one of these peaks as well, and it'll track that, which is often kind of handy. So one thing, for example, that we might want to do is drag this cursor up here, and then we might say, give me the marker A, and then give me marker B. We'll do that. There we go. Sweet. And so now I've basically got two, real-time measurements of the power of the fundamental tone there at 150 megahertz, as well as this sideband at 155, which appears to be moving up and down, which is all right. Sweet. So what else is there that's awesome about this? So yeah, there's some pretty cool stuff here. So, you know, if you wanted to measure things like total harmonic distortion, then you could do that. 3 dB width, which is handy. You know, signal to noise ratio is another handy measurement to have around. So what we might do is, if I remove all markers, drag one up here, and then let's say on marker A, I want to measure signal to noise, then it's going to come along and actually, you know, give me the best estimate as to what that is. And so I'll quickly have a look here and see what the measurement is, and it's pretty close. So if I did it with cursors, it appears to be, so what I've done here is actually set this bottom one as a reference. And then this one at the top is tracking the maximum. And so the measured SNR here, based on that reference, is 38.85, but the actual cursor measurement here is sort of figuring out to be about 39.5, and it's doing a calculation of the actual noise in this span here. So that's pretty clever. Also a very handy tool to have. Cool. So I think that's about it. The last thing that's, you know, somewhat worth looking at is, if I turn averaging off, turn that back to manual, we'll zoom right in on this guy that's moving around here. And what I'll do is I'll quickly just remove that. I'll get rid of all my cursors. And what I want to do is drag a marker up onto this and trace it. So what I'm going to do is add the measurement for that marker A. I'm going to track its frequency, and then I want to show a trend of it. And you'll see that what's happening in this graph is it's just showing me the trend of what that particular measurement is doing. For example, if I were to add another marker here, and I wanted to look at the frequency of the peak, it should, in theory, give me the same thing. But what this is doing is actually not looking at a marker, it's just looking at the data and trying to figure out what the peak frequency is. So if there were multiple peaks on this spectrum, this marker here would just be giving me the frequency of whatever the largest one was. But I can also do SNR, I can look at noise level. But, you know, what I'm also interested in, for example, is looking at something like the power, and that should remain relatively constant. So now we've got a dashed line that appears down here on the trends window, and that is just going to show me that the power in that particular tone is not changing over time, but its frequency is. All right, so that's cool. And then I suppose the last neat thing to look at is, if I zoom out like this, is if I hold down on the traces, I can put in waterfall view. And so what this actually does is brings up what is called a spectrogram. And this is essentially the spectrum over time. And this can be a really, really cool way of visualizing, you know, time varying features in your signals. So we can definitely see that, you know, oscillatory behavior of that signal on channel 1, but, you know, the signal on channel 2, the blue one here, is not really doing too much. Although if we zoom in, you can kind of see some sinusoidal modulation on the amplitude of those sidebands. And so you can see that this waterfall view just gives you a really intuitive snapshot into the time varying characteristics of whatever signals you're viewing, which is, again, extremely handy and also kind of cool to look at. So I guess there's that as well. So to exit out of this, just quickly, you can actually still save data from here. But to exit, you just click the X button, and then we are done. And then, of course, if we want to get back out, switch our instruments or just go back to the main menu, just hit this, and then off we go. Sweet.